All right, this is the group quiz that you took right before Thanksgiving break. It was about searching for the pearls. So the problem was that you need two pearls between 7 and 9 millimeters in diameter. We know that the pearl sizes are approximately normal with a mean of 8 millimeters and a standard deviation of 2 millimeters. We want to know how many oysters we should expect to open until we find two of the appropriate size. And so this problem takes the tact of using simulation to try to figure this out. So part A said determine the probability of finding a pearl of appropriate size. So the way I'm communicating this is that the size of a randomly chosen pearl I'm calling X. We know X is approximately normal with that mean and that standard deviation. This is what we're trying to find, the probability that X is between 7 and 9. So I drew a picture of a normal curve, and I'm going to find this area under the normal curve. This is a fairly standard normal problem. In order to do that, we need to find the z-scores. So the standard deviation is 2, so if we're 1 above the standard deviation, that's a z-score of 1/2. And if we're 1 below, that's a z-score of negative 1/2. And so ultimately, we're finding the area under the standard normal curve between those two z-scores. Remembering that we use the function normal EDF, and we get our answer 0.383. However, if we're reading the question carefully, it says round this probability to the nearest tenth. And so our final answer for part A is 0.4. And that rounding is going to affect the rest of the problem here, especially in part B when we're designing a simulation for this probability. Okay. All right, that was part A. Most groups did pretty well with that. So we move on to part B. Part B was describing how you would use a table of random digits to carry out a simulation to determine the number of oysters needed to find two of the appropriate size. So first of all, we're going to use one digit to represent a pearl, because that probability that we're representing is 0.4. Okay? If you didn't round appropriately in part A, then, for instance, you left it as 0.38, then you would have had to use two digits here. This is why it told you to round. However, if you didn't round correctly for part A and you did part B correct based off what you did in part A, you were fine for part B. Okay, so first of all, we're simulating a 40% chance. So 4 out of the 10 digits from 0 to 9 should be coded as a pearl of appropriate size. So I'm saying that's 0 to 3. And then the other ones from 4 to 9 are not appropriate size. All right. So we need to explain here that we're looking at one digit at a time from right to left, from left to right, until, this word until is key here, we see two that are between 0 and 3. Repeats are okay. And then we're going to count how many numbers we looked at. And then we're going to repeat that many times. Really important, when you talk about designing the simulation, you should always add at the end that you're going to repeat your trial as many times as you can. Okay? It does no good, really, to do a simulation once. That's one trial there. It's to repeat it many times. Okay, so now we need to take our description and actually just exactly follow it here. And run 3 trials of our simulation. And most people were fine on this. So we said 0 to 3 was good, and 4 to 9 was not. Okay, so I look at this, it's not good, 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 boom. And then finally we get those two. So how many pearls did we look at? We looked at 5, 10, 12. Okay, second trial, we've got this one and this one. It took us 5. The third trial, we got this one and this one. So that took us 8. All right, so pretty simple there. Now we move on to the question that actually matters. So part D shows the results of 2 100 trial simulations. So we did 3 trials. Okay, we got results of 12, 5, and 8. If I made a histogram of that, I'd have a bar at 5. At 8, I'd have another one, and then at 12, I'd have another one. Well, we just continued this process 100 times until we got histograms that looked like this. Okay, one of them was the simulation where we're looking for oysters between 7 and 9 millimeters. So the scenario we just did. And the other simulation was looking for pearls between 4 and 6.5 millimeters. Okay, and so we need to figure out which one represents which, and more importantly, why. Okay, so let's look at an individual pearl. All right, we know that an individual pearl has a mean of 8 and a standard deviation of 2. Okay, so this is like 10. This is like 6. Okay, so where is 4 and 6.5? 4 is here, and 6.5 is roughly around here. So I guess the question is it more likely to find a pearl between 4 and 6.5 and 7 and 9? Okay, now 4 to 6.5 is a range of 2.5, whereas 7 to 9 is a range of 2. So maybe it seems like that it's more likely to find between 4 and 6.5. All right. However, we also know that between 7 and 9 is where most of the area is. It's concentrated in the middle here. It's unimodal and symmetrical around 8. Okay, so really, in order to know for sure, we should compute the probabilities of finding each one of these things. So if we find between 7 and 9, we found in part A that there's about a 40% chance of finding a pearl of that size. All right, so let's do the same thing for 4 and 6.5. So I have to find a z-score for each. Okay. All right, so I did the same thing that I did to find the probability between 7 and 9 in order to find this probability. So I found the z-score for 4, which is -2, and the z-score for 6.5, which was -0.75. And if you're like, well, how did you get that? It's 6.5 minus 8 over 2. That's how I got that. I put that in the calculator, and I found that this probability was 0.2, I believe. So it's more likely to find a pearl between 7 and 9 millimeters than it is between 4 and 6.5. So that's going to help us figure out which one of these is the one we want. Okay, so the question says which one is between 7 and 9. So if it's more likely to find between 7 and 9, it's going to take us on average less number of trials to open, or less number of oysters in order to find 2. So if I look at this, I see that this one I get up to 30, and there's a lot more in like the 8 to 10 range, whereas here the maximum is 14, and there's a lot more in the 4, 5, 6 range. So this must be the one that's between 7 and 9. So the correct answer here is A, and really what you needed to say was because it's much more likely, or it's more likely to find a 7 to 9 millimeter pearl than a 4 to 6.5 millimeter pearl. And therefore, on average, it will take less oysters. And A matches this. This is if you did the other one. Okay, so now part E says use the distribution that you picked in part D in order to compute the expected number of oysters to find 2 pearls between 7 and 9 millimeters. So basically what we're doing is we're finding the average from distribution A. Okay, and I guess the way to look at it is that there's 100 trials that we ran here. So if I'm going to find that average, I'm going to divide by 100. 9 of the trials, it took us 2 oysters. So basically, I'm going to do 18 plus, well, 22 times it took us 3. So I'm going to add 22 times. So that's why I'm doing this. This sum is 66 plus, and I continue in this fashion. 4 times 20, which is 80 plus dot 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 dot, and you end up getting, what is it, 5.16 when you do that. Most of you were pretty good on this, at least in my class. If you happen to pick the wrong distribution, as long as your work reflected that, you're fine. And if you picked the wrong distribution, I think your answer was 9.13.